Okay, so when we left off, we had just run this zero inflated negative binomial regression. And so let's kind of go back and take a look at what all this means. Remember when we specified this, we specified the inflation to go with the number of responders. Essentially what this inflation part of the model does is it's used to predict whether there was a 0 event or whether there was a 1 event. So essentially what negative binomial does, or the zero inflated negative binomial does, is it sort of pairs a logit model, like a dichotomous logit model, along with an event count model. And so they essentially specify this logit model, this number of responders and a constant, to determine the likelihood of the event being a 0, right? And then what they do is they do the second part of the estimation is these dichotomous variables on the number of events that actually happen. So it sort of bifurcates the estimation process. And because of that, it's as we'll see, it's a little harder to, like, you can't get residuals for this model because it's actually two models kind of tied together. And so when we think about kind of diagnosing heteroscedasticity and that kind of stuff and plotting the residuals, we can't do that for this model. And so there's certain limitations, but it really is useful in that it gets rid of that over dispersion problem of having so many events without injuries and then just having a marginal few, right, that do have injuries. And again, that's a good thing in real terms in the case of our project, but that's just kind of the modeling trying to adjust to that to the situation. So we'll see here, we've got, if we go back, we'll see we have fire control, search and rescue are both significant, reasonably large coefficients there. Hazard, again, shows some marginal strength, and so does fire rescue hazard, and the rest of these, SNS and standby, are all minimal. In terms of the estimation, these values down here are the parameters for the functional form. If we go up and look at the previous one, right? So we had those up here too, right? And so you know that these values coming back and being important tell you that that you need to use a negative binomial versus a Poisson. So down here you see this likelihood ratio test. That's essentially a likelihood ratio test between the negative binomial and the Poisson that we did up above, right? So in the Poisson, that alpha value is essentially 1. It doesn't have that extra alpha value, and so that's what we do. That's what we're doing with the negative binomials. We're adding these kind of two parameters associated with a more flexible functional form. Here, what we'll do is we'll go down and we'll see that we do have these kind of same values. They actually, notice, however, though, they reduce in size, right? So so it was about 2.5 and 11, right? Whereas up here it was 4 and 62. You see that 62 is really telling you that you got that over dispersion problem on that 0 category. So by including this logit aspect to first weed out the events that aren't likely to have any observation other than 0, then we were able to kind of clamp down that alpha and fit the data a little bit better. And again, we know that the zero inflated works better versus the standard because we have this Wong test down here that does ZNB versus the standard negative binomial. We have a z statistic there, and we have a probability that is much less than 0.00 or 0.01, and that tells us, yeah, we needed this additional kind of inflation control in here in order to model this appropriately. Okay, good. The other way that we know, of course, is the AIC value and the log likelihood value, but basically the Wong test here is telling us, yeah, we needed to do this inflation. Yeah. So we've got that out of the way. Let's work with this a little bit. And so the first thing that I want to do is when we do this Wong test, it limits you from being able to do certain things with the residual with the standard errors that are actually very beneficial. We've always been concerned a little bit about heteroscedasticity, and so one way to control or counter the detrimental effects of heteroscedasticity is we can use robust standard errors. And so what it is, it's a clustering process within the estimation sequence that clusters on kind of random sequences, and it helps control for aspects of residuals and may give us a little bit better estimates. And so one thing I want to do is I want to try this with robust standard errors and see what we get. So let me go back down here. Let me arrow into this command structure. I'm going to hit function up. I think you just hit page up and it'll work. I'll show you. If I keep Wong in here, and if I put VCE, which is the structure for telling you to do robust standard errors, if I put both of those in there, it'll come back and it'll say I can't do it with Wong. Right? See, the Wong statistic cannot be computed with constraints VCE cluster or VCE robust. And so what that's telling me is I just simply can't do what I try to do. So what I'll do is I'll go ahead and get rid of that Wong test. And it doesn't matter. We know we've run it, and we know now that we need to have the negative binomial. Changing the robust standard errors isn't going to change that test at all. But it will give us a little bit better evidence in terms of the estimates. And so let's go ahead and click return and let this thing run. It really does. It's 20,000 iterations, and there's a kind of complex two-stage model here, so it takes a while to run. You'll get to this point where you hit more, and so what I always do is I hit just hit one letter on your keyboard. I always do F fitstat to do the AICs and everything else afterwards, and then that brings up the rest of the model. So let's let that run and see where we're at. And it takes a while. Okay, so again, notice here that the AIC didn't change at all, and neither did the log likelihood. They're still 402 and 824. The specification of the robust standard errors doesn't affect the log likelihood specification. But what it does is it gives us a little bit of control for heteroscedasticity, and it may give us, counteract negative aspects of heteroscedasticity or give us an advantage. It's always a good idea to run with them. And so again, here you'll see, right? So we still have the same parameter size, but look at the standard errors with these robust standard errors. Note that it's robust, right? Now we're highly significant there. We're highly significant for search and rescue, and we have evidence of significant relationships for both hazard and now fire rescue hazard. These are less than 0.10, so essentially they're significant at a probability 0.05 level with a single tail test, essentially. So these are significant no matter what, but these show some anything less than 0.10 is significant at 0.05 with a one tail test. So we can actually draw some inferences on all four of these categories now because we went and used robust standard errors. Okay. As we go forward here, let's go through, and I'm going to run a series of predictions, and we're going to do some marginal effects. And so that's a little bit of a complex process, so I will probably leave off right about here.